Hey there students, welcome to part 2 of the video series on improper integral type 2. The integrals that contain an infinite discontinuity or a vertical asymptote within the domain of integration. Okay, so in this case we're going to be looking at a case where we have an interior infinite discontinuity. In the previous clip we looked at a case where we had a left endpoint on discontinuity. So in this case we're going to look at an interior infinite discontinuity. Okay. All right. So as we discussed in the first clip, an infinite discontinuity within the domain as opposed to at the endpoints involves a combination of a left and a right endpoint discontinuity. Okay. So write down the example. This is example two. Example two, and we're going to evaluate the integral. Evaluate the integral from 0 to 2 of 1 divided by the third root of x minus 1. Alright? So when you take a look at this integral, if you inspect it for a minute, you notice that there is an infinite discontinuity at x equals 1. Okay? Because that makes the radicand of the denominator to become 0 if x is 1, and then 1 over 0 you have an infinite discontinuity. Alright, so what we're going to do, let's draw our domain of integration. Our domain of integration is from 0 to 2, 0, oh, let's call it 1, 2, 3, 4, 1, 1, 2, 3, 4, 2. Alright, so we have the infinite discontinuity at 1. So what we're going to do is we're going to pick a c value, and um, we're going to, oh, let's call it a d value. Okay. All right, let's scroll down. We're going to call it a d value because that's basically what we use in the formula. We're going to stay consistent here. So we're going to pick a d value, and on the first integral, d is going to approach 1 from the left, and then on the second integral, d is going to approach 1 from the right. Okay, now we're going to take these two limits of the integral from 0 to d, and then from d to 2. All right, so let's go ahead and apply the formula for improper integrals, where the domain is where the discontinuity is in the interior. So that's going to give us the integral from 0 to 2 of 1 over I can express this as x minus 1 to the 1/3. It's easier to integrate when I write it like that. Okay, dx equals the limit as d approaches the discontinuity from the left, which is 1 from the left. Actually, I got my notations switched around. This is approaching from the left. Yeah, that's right. Okay, from the left of the integral from d, from 0 to d, from 0 to d uh, of 1 over x minus 1 to the 1/3 dx. Okay, this integral represents this area right here. We're going from 0 to 1. Since we can't get to 1 because of an infinite discontinuity, we're going to we're going to go to d, okay, from 0 to d, and then we're going to let d approach 1 from the left. All right? Plus, now we have to do this area on the right side. Okay, so it's going to be the limit. We're going to, in this case, now let d approach 1 from the right. Okay, our integral. Now we're now going to go from our d, which approaches the 1, all the way to 2. Okay, so from d to 2 of 1 over x, let me write it again, x minus 1 to the 1/3. Okay, x minus 1 to the 1/3. Okay, dx. All right, so what we're going to do now, we can basically evaluate this integral and then plug it back in and then use FTC part 2 to finish it off. Okay, so let's go ahead and evaluate what this integral is first, and then I'm going to put it back into the problem. All right, so what is the integral from, what's the integral of 1 over x minus 1 to the 1/3 dx? Well, I can rewrite this as the integral of x minus 1 to the negative 1/3 dx. Okay? Now I can use the u substitution. I'm going to let u be x minus 1. Okay? That makes du dx. All right, so using u substitution, I'm going to have the integral, I call it changed. I'm going to have the integral from, integral of u to the negative 1/3 du. All right, I'm going to change my variables back because I don't want to change the limits of integration. Okay, so now applying the power rule, we know what the power rule for integrals is, right? So if you integrate x to the n dx, is basically x to the n plus 1 over n plus 1. Okay, so that's what I'm going to apply here. So if I apply that here, I am going to have u to the negative 1/3 minus 1, plus 1 over negative 1/3 plus 1, right? So that's going to give me u to the 2/3 over 2/3. And then when I multiply the numerator by the reciprocal of the denominator, I have 3 over 2 u to the 2/3. Okay, so just reciprocate this and multiply it by the numerator, and then get that, okay, which is equal to 3 over 2. Remember what u is? U is x minus 1 when we're doing a u substitution here. So 3/2 of x minus 1 raised to the 2/3 power. Okay, so this is the value of the infinite integral. Now what I'm going to do is I'm going to put this back into the problem, and I'm going to evaluate this for respective limits of integration using FTC part 2. Okay. All right. So I'm going to go ahead and erase this, and then I'm going to scroll up and put our answer into the problem. Okay. All right. So let's see, what do we have here? We have these two integrals, limits of integrals. So we already know what the value of the infinite integral is. So we're going to have the limit as d approaches 1 from the left of 3 over 2 x minus 1 to the 2/3. Using FTC approach, we're going to evaluate this from 0 to d plus the limit as d approaches 1 from the right of the same derivative, 3 over 2. The value of the antiderivative, 3 over 2 x minus 1 to the 2/3, and we're going to evaluate that from d to 2. Okay? Alright, so let's go ahead and work this out. So let's start with the left one. So we're going to have the limit as d approaches negative, as d approaches 1 from the left. I'm going to plug in the upper limit and then the lower limit, okay? So when I plug in the upper limit, I'm going to have 3 over 2 times d minus 1 to the 2/3 minus, when I plug in the lower limit, I have 3 over 2 times times 0 minus 1 to the 2/3. Okay. All right, and then on the other side, plus the limit as d approaches 1 from the right of, plugging the upper limit, 3 over 2 times 2 minus 1 to the 2/3, okay, minus 3 over 2, plugging the lower limit of d minus 1 to the 2/3. Okay, so there you have it. All right, now let's go ahead and simplify a little bit, and then we're going to evaluate the limit, okay? So we have the limit as d approaches 1 from the left of 3 over 2 times d minus 1 to the 2/3 minus 0 minus 1 is negative 1, right? So we have 3/2 times negative 1 to the 2/3. And then here we have the limit as d approaches 1 from the right of 3 over 2. 2 minus 1 is just 1 of 1 raised to the 2/3 uh, minus 3 over 2 times d minus 1 to the 2/3. Okay. All right, now we can take the limit where applicable and simplify where applicable. Okay, so here I'm going to take the limit as d approaches 1 from the right. So we're going to have 3 over 2 times, let me code this so we don't get confused. 1 from the left, okay, minus 1 to the 2/3. This is independent of d, has no d in it, so let's just evaluate it as it is, okay? So negative 1 raised to the 2/3, let's do that here. So negative 1 raised to the 2/3 is the same thing as the cube root of negative 1 square, right? Cube root of negative 1 is negative 1. If you square it out, you get 1, all right? So if I evaluate this whole business right here, this piece becomes 1, so just 3 over 2 times 1. It's independent of the limit, so the limit doesn't apply to this because it doesn't have a variable, okay? All right, done with that for now, plus this is independent of the limit. 1 to the 2/3 is um, just 1 because we're just doing 1 to the 2/3. Applying the rational roots property of exponents, we just have the cube root of 1 square, which is just 1, right? We all know that. This is independent of the limit, so we'll leave it alone as 1. Now this, we have to take the limit upward, so it's going to be minus 3 over 2 times d is going to be, we're now going to be approaching 1 from the right, okay? Minus 1 to the 2/3, close that out. Okay, now what do we have here? So this is going to become 3 over 2, 1 from a very small negative number. If we subtract 1 from it, we're going to have a very small negative number, okay? A very, very infinitely small negative number like 0, really, really close to 0, raised to the 2/3, minus, this is just 3 over 2, plus, what happened here? What happened here is that I lost my 3/2, so I'm put it back in. 3 over 2 times 1. Okay, so if I multiply that out, I'm going to have 3 over 2. Sorry about that. Minus 3 over 2 times, this is going to be a very small, extremely small positive number. Okay, as close to 0 as it gets, raised to the 2/3. Okay, now if you take the 2/3 roots of an infinitely small positive number, you're going to end up with something like a really, really small number like 0. Okay, so this is going to be 3 over 2 times 0, really, really small, minus 3 over 2 plus 3 over 2 minus 3 over 2. You take 2/3 roots of a really, really small number, it's still going to be like 0, really close to 0. So if you multiply this, you have 0 minus 3 over 2 plus 3 over 2 minus 0. Okay? The direction you're approaching 0 doesn't really matter here because it's really, really small and you're not reciprocating anything, okay? So when you evaluate these two interior pieces, you're going to end up with the whole thing becoming 0. All right, so that's basically the value of the integral. The integral from 0 to 2, 1 over the cube root of x minus 1 is in fact convergent. It converges to 0. And that's the value of the integral, which is the value of the area. Okay, so there you have it. All right, so let's take a look at the graphical representation of the problem we just did to help solidify our understanding. This is a function that we were evaluating the integral of. So this is f of x, which is 1 over the 3rd root of x minus 1. So we're evaluating the integral from 0 all the way to 2. Okay, so we can clearly see that we have a infinite discontinuity or vertical asymptote at 1. Okay, so what we chose to do was to evaluate the integral from the left and the integral from the right. So the first integral we did was the integral from 0 to 1. So that was this piece right here. Okay, so this is the integral from 0 to 1. We did the limit as d approached 1 from the left of the integral from 0 to 1 of f of x dx, right? That's what we did for the first one. And this one had a value of 3/2. Okay. So this integral actually is convergent. Remember, both of them have to be convergent in order for the final result to be convergent also. And then we also did the right side, the integral on the right, uh, this piece right here. I'm sorry, this is negative 3/2 is downstairs. And then we did this piece right here, which is the limit of an integral, because we have a infinite discontinuity on the lower bound or lower limit of integration. So we had the limit as d approached the infinite discontinuity, which is 1 from the right, of the infinite integral of d all the way to 2 of f of x dx. Okay. This one we're going from 0, we can get to 1, so we're going to make it d. Okay, 0 to d. All right, and then when we evaluated this integral, we got 3/2. So you see that these two areas are identical, so when we added them up, that's why we had negative 3/2 plus 3/2. The answer was 0, okay, because we have exactly equal areas on both cases, okay? So there you have it. So thanks so much for taking the time to watch this video. Please feel free to subscribe to my channel by clicking here, so you can get updates to other cool clips such as this. If you like this video, you can click like down here. I really appreciate it. And please, please, please comment down here. Tell me what you think about this video so I can make improvements in the future. More videos can be found on my Thanks again and have a wonderful day.